The voltage drop observed when starting the 60 horsepower 480 volts three-phase motor while connected to the 80 kilowatt generator is characteristic behavior. Starting a large motor places a significant burden on the power source, particularly a generator. The initial inrush current, which is the current drawn by the motor when it first starts, can be several times higher than the motor's normal running current. This inrush current causes a substantial voltage drop across the generator's internal impedance. The generator essentially cannot instantaneously supply the required power surge and the voltage sags as a result. A voltage drop from 475 volts to 350 volts upon motor starting suggests the generator is undersized relative to the motor's starting demand. Simply adding a time delay to the phase monitor will not address the underlying problem of insufficient generator capacity. The phase monitor is designed to protect the motor from operating under single-phasing conditions, where one of the three phases is lost. Running a three-phase motor on single phase can lead to overheating and rapid motor failure. Disconnecting the phase monitor allows the motor to start, but removes the protection against single phasing. This is not a desirable solution. The brief voltage drop itself is unlikely to immediately damage the motor directly, but extended or repeated voltage dips can stress the motor's insulation and potentially shorten its lifespan. More importantly, the voltage drop could adversely affect sensitive electronic components, particularly those in a motor drive if the motor is equipped with one. These components are designed to operate within a specific voltage range, and a significant voltage drop can cause them to malfunction or even be damaged. The primary issue stems from the generator's inability to adequately handle the motor's starting current. The most effective solution involves increasing the size of the generator. A larger generator possesses a lower internal impedance and greater power output capacity, allowing it to deliver the necessary starting current without experiencing a drastic voltage drop. To properly size the generator, one needs to consider the motor's starting kilovolt amps, or kVAR, which is often provided on the motor's nameplate or in the manufacturer's specifications. If the motor's locked rotor amps or LRA are known, the starting kVA can be calculated using the formula kVA equals volts times amps times the square root of 3 divided by 1000. The generator's continuous power rating must exceed the running load of the motor and any other connected loads, and its surge capacity must be sufficient to accommodate the motor's starting kVA without excessive voltage drop. The allowable voltage drop during motor starting is often specified by industry standards such as the National Electrical Manufacturers Association, or NEMA. These standards typically recommend limiting the voltage drop to a certain percentage of the nominal voltage, such as 15% or 20%. A qualified electrical engineer can perform load flow calculations to determine the appropriate generator size and ensure compliance with relevant standards. If upgrading the generator is not feasible, other mitigation strategies can be explored. Firstly, consider using a reduced voltage starter. Reduced voltage starters, such as autotransformers, power winding starters, or solid-state starters, reduce the voltage applied to the motor during startup, thereby lowering the inrush current and the resulting voltage drop. These starters introduce additional impedance into the motor circuit during starting, gradually increasing the voltage as the motor accelerates. Secondly, a soft starter could be used. A soft starter is a type of reduced voltage starter that uses solid-state devices, such as silicon-controlled rectifiers or SCR, to control the voltage applied to the motor. Soft starters offer smooth, stepless acceleration and deceleration, minimizing mechanical stress on the motor and driven equipment, as well as reducing voltage disturbances on the power system. Thirdly, investigate using a variable frequency drive, or VFD. A VFD controls the motor's speed and torque by varying the frequency and voltage applied to the motor. VFD can significantly reduce the inrush current during starting by gradually increasing the motor's speed from zero. VFD also offer energy savings and improved process control. Another option is to implement power factor correction. Improving the power factor of the system can reduce the overall current draw and voltage drop. Power factor correction capacitors can be installed at the motor or at the generator to improve the power factor. These capacitors supply reactive power to the system, reducing the amount of reactive power that must be supplied by the generator. Improving the power factor can also reduce energy losses in the system and improve voltage regulation. Another approach is to use an isolation transformer. An isolation transformer can isolate the motor from the generator, reducing the impact of the motor's starting current on the generator. The transformer can be sized to provide a voltage boost to compensate for the voltage drop. The transformer also provides additional protection against voltage transients and harmonics. To address the phase monitor issue, installing a time delay relay on the phase monitor may seem like a potential workaround, but it needs to be carefully considered. The purpose of a phase monitor is to detect single phasing and other voltage imbalances that could damage the motor. A time delay relay would temporarily disable the phase monitor during motor starting, allowing the motor to start even if there is a voltage imbalance. However, this approach carries the risk of leaving the motor unprotected against single phasing for the duration of the time delay. If a single phasing condition occurs during the time delay, the motor could be damaged. A more sophisticated approach involves using a phase monitor with an adjustable time delay and sensitivity settings. These monitors allow you to set the time delay and voltage imbalance thresholds to minimize nuisance tripping during motor starting while still providing adequate protection against single phasing. The time delay should be set long enough to allow the motor to start and the voltage to stabilize, but short enough to provide timely protection against single phasing. The voltage imbalance threshold should be set high enough to avoid nuisance tripping during normal voltage fluctuations, but low enough to detect single phasing conditions. Furthermore, it is crucial to ensure proper grounding of the motor, generator, and associated equipment. A good grounding system provides a lower impedance path for fault currents, minimizing voltage drops and protecting against electrical shock hazards. The grounding system should comply with applicable codes and standards, such as the National Electrical Code, or NEC. Article 250 of the NEC covers grounding and bonding requirements. Regular maintenance of the motor, generator, and associated equipment is also essential. This includes inspecting and testing the motor windings, bearings, and insulation, as well as cleaning and tightening electrical connections. Regular maintenance can help prevent motor failures and ensure reliable operation. When evaluating these solutions, it is essential to consider the cost, complexity, and potential impact on the overall system performance. A qualified electrical engineer can provide valuable assistance in assessing the situation and recommending the most appropriate solution. The engineer can perform calculations, conduct site surveys, and evaluate the existing electrical system to determine the best course of action. They can also ensure compliance with applicable codes and standards and provide guidance on the installation and commissioning of new equipment. In addition to addressing the voltage drop and phase monitor issues, it is also important to consider the overall reliability and efficiency of the electrical system. This includes evaluating the power quality, harmonic distortion, and energy consumption. Power quality problems can lead to equipment malfunctions, reduced equipment life, and increased energy costs. Harmonic distortion can cause overheating of transformers and conductors, as well as interference with sensitive electronic equipment. Energy consumption can be minimized by using energy-efficient motors, drives, and other equipment, as well as implementing energy management strategies. A comprehensive electrical system evaluation can identify potential problems and opportunities for improvement. This evaluation should include a review of the electrical drawings, a site survey, and measurements of voltage, current, power factor, and harmonic distortion. The results of the evaluation can be used to develop a plan for improving the reliability, efficiency, and power quality of the electrical system. Addressing the motor starting voltage drop and phase monitor issues requires a comprehensive approach that considers the motor, generator, and overall electrical system. A qualified electrical engineer can provide valuable assistance in assessing the situation and recommending the most appropriate solution. Remember, safety is paramount when working with electrical equipment. Always de-energize circuits before working on them and follow proper lockout-tagout procedures. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. If you are not qualified to work on electrical equipment, consult a qualified electrician. In summary, the motor starting voltage drop is common when using generators and large motors. Firstly, increasing the generator size is optimal. Secondly, consider a reduced voltage starter. Thirdly, analyze using a VFD. Fourthly, evaluate power factor correction. Fifthly, potentially employ an isolation transformer. The time delay on the phase monitor can work, but it is important to ensure it is sensitive enough that it protects the motor from single phasing.